Do you see the presentation screen?
Yep.
Okay.
Yes.
Yes.
So let's continue with this. So because we've seen last time at the end of the lectures, and because probably during the labs you've already got over this programming part, let's see shortly the TCP programming API, and then we will shortly discuss a little bit about the two protocols, TCP and UDP, that are both working over this. Where is my? Okay, so both TCP and UDP will actually be handled by these APIs. So we have a number of API calls that are present on both Windows, Mac OS, Linux, and so on. It's part of the TCP IP programming API and are present on all operating systems with more or less, with slight differences from time to time. So you have them here in categories of APIs that are likely used in the client and the server, only client, only server, client, and the server. So the first call will be the socket call that has as a first argument a protocol family. Okay, in our case, or address family, sorry, it will be AF INET here at all time. As you will see during the programming part, this one here, it will be in most times AF INET. You won't be using with anything else, just with, this is for TCP IP. The type, this will be either SOC dgram or SOC stream. This one is TCP. This one tells us to create a UDP socket. And the protocol, usually you leave it 0. It's a flag that you don't use normally. And this one creates a socket. The socket is the entry point into the TCP/IP communication protocol. Programmatically, it allows you to send data and to receive data from other applications. What TCP allows us, it allows us to do some sort of inter-process communication between processes that are not on the same machine, as you have learned up until now at operating systems with pipes, named socket, named pipes, unnamed pipes, shared memory, and so on. But it allows you to do communication between processes that are running on different machines, interconnected by a TCP/IP network. Then the connect call, the first argument is a socket created with a socket call before. It allows you, when dealing with TCP, this is what we are dealing right now in the first lectures. It's to create a connection, a TCP connection, between your process here and a process on a different machine that is identified by this argument here. This encode the IP address and the port of the remote process. Okay, in this structure, you'll put the IP address and the port. And then the third argument is the length of this structure. Is the length of that. It is used by the connect call because the connect call, it's used not only with TCP/IP but with some other protocols, and that those protocols have different lengths for these structures. I mean, this structure can accommodate multiple protocols, and the length actually tells the connect call. It's one of the hints to the connect call that tells it how much data to use and in which way from this structure. Then we have the bind call. Now, I believe that you were explained during the labs what bind does. Can somebody tell me? Again, it takes a socket here. As you can see, the following calls, they all take as first argument a socket, so I won't insist into that. This one is a socket, this one is a socket, this one is a socket, this one is a socket. So once a socket is created and initialized in some way, well, the first argument to almost all the other calls, it will be the socket. So what bind does? Can somebody explain me from what you've?
I think bind associates a port to a socket.
Exactly.
Or a socket to a port.
So you should know that whenever a socket is created, here this one gives out or spits out a socket. And that socket already has some IP of the local machine assigned to it. And it also has a port. Only that initially this one is a random free port. Okay, a random value. Now with bind, what you do is you can change this value here to something on purpose. For example, if you want to bind your socket to port 1200, well, initially when you create a socket, you cannot be sure that this is the value that you will be assigned. So if you want, for example, clients to be able to connect to you, you will need to agree on the port numbers your server will be running. If not, clients won't be able to connect you because they don't know where to call you, on which port to connect you. So actually, when you create a socket on a server application, you already have a port, only that it's a random port. If you want to fix it at some predefined value, you call bind. And in bind, you specify here the IP addresses and the port, the IP addresses and the port where that socket will be bound. You could have, for example, a computer with multiple network cards with multiple IP addresses. You can tell here that you only want to listen on a specific IP address or on all of them, and you also give the specific port on which you're listening, and that's bind what it does. Bind, it returns, it has some return value when that is negative. Usually it's 0 when everything happens correctly. When negative, then you have an error. And the most typical error is that you're trying to bind to a port which is already used by another process, by another socket. By that means not necessarily a different process, but a different socket. Then you have the listen call. The listen call, it's only used on a server-side application, and it establishes for a socket, for a listening socket, for a socket that will be used to accept incoming connection, to establish a queue, and it gives you the queue length. Now to the group that I had lab with, I explained that this queue is used by the TCP, for example, to place all the incoming connections that are coming right at the same time will be placed into that queue and served by the operating system from the queue as soon as it can. You know, they are going into the queue. They are going that way, and the operating system is taking them out that way. And the operating system takes the first entry and connects it. Then it takes the second one and connects it, and takes the third one and connects it, and so on. Why do we need that queue? But think of it of a web server. A web server, for example, Google.com, it has a high probability of being connected by thousands of people at the same time. So if you wouldn't have that queue, or if this queue would have a length of 1, just like this, the first client that will come in will be served by the operating system, and all the others will be rejected because the operating system won't have time to handle them in a timely manner so that the connections are accepted. So this is just a preparatory place where connections are placed and served by the operating system. The higher the contingency on your listening socket is, well, the higher that value here, this value here should be. If you have a server that you expect to be connected at the same time. We're just talking about simultaneous incoming connection requests. So the higher that number is, the higher this value should be. Okay, it doesn't do anything physically. It doesn't engage any process on this socket. It only creates a queue somewhere into the operating system kernel memory with that size. I mean, and even this is taken just as, this is just a hint to the OS, because the OS, if you give here, for example, a value very large, like 4 billions, the operating system might not have enough memory to allocate that queue for you. So this is just a hint. It might be used by the operating system or it might not. It will just allocate a queue which is large enough, or which is large, as large the memory it's willing to allocate to your socket. So it doesn't do anything differently than this. Okay, so it's only used on server side because there you're accepting connections, and it actually instructs the operating system to create a queue. And then you have the accept call. The accept call is used on a socket which is called a rendezvous socket, a socket that you have bound on a bound socket, usually, so that you know the port. And when you call accept on a socket, it's actually at that time that the operating system starts listening for incoming connections, for incoming clients. It's only upon calling accept that the client will be able to connect, to call connect and connect to your socket here. While you haven't called accept on a rendezvous socket, on a socket on a server side, let's say, no client will be able to connect with you, even though you have set up a queue. It's accept that actually triggers inside the operating system the process of go and inspect that queue and see if there are any incoming connections and take one and serve it, and so on and so on. Okay, so you can try that if you want. Try to set up a queue with a length of 2, for example, just like that. Into the server and try with 2 clients to connect with it. Probably you will succeed. I mean, your connect calls, they won't return an error right away. But if you don't call accept on the rendezvous socket on the server side for 5 minutes, these 2 clients that have called connect and tried to connect to the server, meanwhile, while the server hasn't called accept, will time out eventually. So they will arrive into the queue. They won't be rejected immediately as with an error, there is nobody listening there, but eventually they will time out. You can experiment that if you want. Now, accept, it takes a rendezvous socket, the socket that you will be listening for connections on the server side. It has 2 these arguments here. These are optional. That means you can give them as null in C, and Python you can omit them. And if you give these, you can see these are pointers here. This is pointer, this is a pointer. You give in, or you fill in the address of a struct sockADDR structure. We will see the one that is here as well, the one that is here as well. So the same here, the same here, the same here. And this structure, if you give a pointer to it and you give a pointer to an integer for receiving the length that will be filled in, the operating system will be filling in here the IP address and the port of the client that is connecting to your server on the rendezvous socket. And the most important thing is that if this thing is negative, that is an error. And if it's a positive value, then this will be a socket. And this is actually the most important thing that you need to remember here, this one. Except in the case of TCP, because it's only used with TCP normally, returns either an error or a socket. So whenever a client tries to connect to your server, the server into the code, when this call finishes, the server would have a new socket created, and that socket will be used to communicate with that specific client. And the original one, the rendezvous socket, will be only used for calling accept again and again and again and again for accepting multiple clients that needs to communicate with your server. So every accept call returns, in the case of success, a new socket that handles the communication with that client. And by the end, a call that it's used by both the client and the server is the close call that takes a socket and actually terminates the connection that has been created by the connect and by the accept calls. Okay, so it just finishes, it tears down the connection. So to sum up, socket, connect, bind, listen, accept, and close. These are connection forming and connection tear down. The structure that we discussed before, the SOC ADDR structure, it has these members. There is the generic struct SOC ADDR structure, which has just 3 fields: a land, a family, which in your case will be always AFINet, some obscure data. This one is something like, let's say, how should I put it? At this level, this structure handles any type of protocol, like defined here, any type of protocol. And then it's this type of data that differentiates between different protocols. Okay, it's just a bunch of 14 bytes, but it gets specialized. When we're talking TCP, this one gets specialized here. How should I throw this? Into these 3 fields. Okay, you get a specialization in 2 bytes, these ones. Okay, 2 bytes. Out of those 14s there will be the port. We have 4 bytes here in the case of TCP. TCP and UDP, that's the specialization, will be the IP address, and there are 8 bytes remaining that TCP and UDP are not using it, and they will just be, let's say, how should I? Unformed data that is not used. TCP and UDP do not need these 8 bytes, but there might be some other protocols that are using those 8 remaining bytes from the SOC ADDR structure, because the generic structure has 14 bytes there for the addressing data, no matter what protocol. TCP uses 6 of them and not using 8 of them. And now, as you can see, the second field here, it's also a structure that gets explained here. The struct INADDR inside the SOC ADDR in is actually it's actually INID. Don't get scared about these data types. This one, it will be mapped. Actually, it will be an unsigned int, or it will be char IP4. Okay, it's a union that gets mapped to either an unsigned int, which will be on 4 bytes, or a char. Oh, come on. Or a char with a length of 4 bytes. Okay, so it's just a union inside that, depending on which field of the union you access, it will give you either access to an unsigned int, either to, I think there is something like unsigned word 2, an array of 2 words. Each of those, it's either 2 words, 4 bytes, it's either 4 bytes, 4 bytes, or an unsigned int 4 bytes. You can look at an IP address either as 2 words, 4 bytes, or an unsigned integer, depending on how you want to handle it. Any questions up till now?
Yeah, I've got a question
Go
about
ahead.
the field SALAN.
SALAN. Yeah, this one.
Yeah, looking on the Microsoft Docs.
Yes.
I cannot find the field. I find it when searching for it online, but I can't find it.
I think the Microsoft operating system is already presenting you this structure here. So take a look for SOCKDDR-N, and you'll find this land.
Yeah, I can't find it. It's only the last 4.
I have an error here because it's not on 16 bits, it's on 8 bits here. Okay, so this field, it's exactly the same here. Is exactly the same. It's a direct one-to-one mapping. It's just a renaming of the same thing. Okay, so you would find it in the documentation. We can look at it later on. It's definitely there.
Okay then.
Okay, any other questions about this structure? It's an important structure that you will be using with both TCP and UDP. So from now on, for about 6 to 7 weeks, you will be using this structure here intensively. Okay, this one presented here. So try to be familiar, try to look inside of it, try to get familiar with it, because you will be actually using all the time this structure. You will be filling in ports and IP addresses at all times. Now, if there aren't any other questions, at 9:26. Once the connection is set up and things are getting simpler here, you could use send or write and pass in. Send is the typical API programming from the socket library, but you can also use write, which is the normal, let's say, API from the operating system for interacting with any input-output systems. Okay, you can use write to write to the console, to the screen. You can use write to write into a file socket descriptor. You can use write to write into the socket descriptor. Send, it's a bit more elaborate, as they both use the first argument, a descriptor. The second one will be a buffer from which it takes data to send. The third argument, it will be some length of your data. And this one has some flags that actually allow you to control the behavior here of these are something which won't be present here. Okay, so those flags are missing into the write call, because the write call is more generic. It's for writing into any descriptor available at the operating system as well, but it doesn't allow you to control these flags. Okay, now these are for sending data. For receiving data, you call either receive. This is from the socket library, or you can call read from the operating system generic APIs. The same. Yeah, go ahead. Yeah, I want you to ask questions like this.
Can't we write into a pipe using scanf or something like that?
Using scanf, you cannot write into the pipe, into a
Or
pipe.
sorry, into a socket. Because I know I can do that to write into pipes, because
With
scanf
scanf,
takes
normally you read from something.
oh,
With
sorry.
scanf, read. Okay.
With printf and scanf to
Yeah,
read
with,
write from.
with printf, printf goes through the standard C library. It's a call which is specific to the C programming language. It's not. It does not belong to the operating system. It does translate to a call. So every printf, if you want, goes translated into the OS to a write, if you want. But it goes to a write printf. If you do printf, the first argument to write it will be 1, which is standard.
Yeah, then I'm sorry, fprintf, because I know there is one where you can set the descriptor as well.
Okay, fprintf, it takes a descriptor, but it's a file thing like this. It's
okay,
not,
so
it's
you
not
cannot give a socket
so
or something.
those are not compatible. Out of a file, you can get out the int descriptor, but fprintf doesn't know how to write into a kind of this. It knows to write into the file, into a file pointer, which gets translated eventually behind to a file descriptor, and it gets a call to a write, but the file descriptor will be again a file descriptor here, which is an integer. Okay, a file that you have opened at some point in time. So that's why you cannot write with fprintf into a socket. Okay.
Yep, I got it.
You can get a handle of the file descriptor because a file, it's a structure. File like that. It's a struct, in fact. And one of its fields is an int descriptor. You can get hold of that descriptor and try to write in it, but not with fprintf, but with this or with this, if you want. But fprintf, as I told you, it handles a struct like this, and it's part of the C library. So it goes through a level of pre-processing, which is typical to the C library, and it might not be compatible with the socket call and so on, with the socket file descriptor and so on. Okay, for example, the C library, so that I'm not that abstract in my explanations. For example, the C library, when you write a string, could decide to actually encode the characters into that string into a specific encoding, something like ANSI or UTF, something that the socket library does not handle, for example. Okay, the C library, when you do an fprintf, a string which has an internal representation into your memory might get translated to ANSI there. So some characters might change while writing. The same happens with UTF, for example. If you use a UTF-16 in order to write, for example, Japanese characters, I don't know how to put, those are represented on 2 bytes at some point in time, and you can get a graphical representation of a Japanese symbol into 2 bytes on UTF-16, and one character like this, it's mapped into 2 bytes. In fact, when writing them down into a stream. So this is more likely a C stream file pointer. This one is a file descriptor. They are different things, right? Was I?
Okay. Yeah.
Clear enough? Okay, so they are situated, if you want, at different layers into the APIs. Well, these ones are C, lib, higher level. This one is operating system level, and I kind of messed up the drawings here, but you get the idea. This is at the operating system layer. It's as down as it gets. Okay, now I told you last time, or I've shown you last time, an example of how do you call a very simple client server. Has anyone had the examples shown during the lab? So that I won't insist on this right now. Or do you want us to compile a client and a server and see how they're working? Anyone? Should I demonstrate you the example that we had last time? I assume you had it presented during the labs. Anyone that didn't have it?
We didn't have it.
Yeah, I would appreciate if you could show us.
Okay. Let's go. So this will be boring for some of you because you've already had that during the lab, but let's maximize this window. Okay, so this is my Linux virtual machine. And let me show you the simplest example that we can have. And that is the example that we had last time. Okay, client server. The example that we had last time is it. I can bring it here. My TCP client and my TCP server. If I copy, paste, copy, come on, paste. And so they are on the desktop. Let's move them into here. Come on, cut. Okay, let's leave them in the home directory, paste. Okay, so my TCP client, my TCP server. Go into the home directory and let's try to build them. GCC, my TCP server. Now, this is a C. There is something you should pay attention to. The C++, G++ compiler, usually it's able to compile both C and C++ sources. But you should pay attention because in a C file, you could write any code you want, even C++. So try to stick to it. If you give it a C extension, try to write in code specific to C language, the C language. If you give it a C++ extension, try to write C++. Or in any case, that's the thing that you can compile. Both of the things will be compilable with G++, but a C++ source code won't be usually compilable with the GCC compiler. Okay, so -o server, that would be used to compile my TCP server. Okay, so this is the example that had a lot of errors. Let's try to fix them. And in order to do that, I would, not this one, I would go here, my TCP server, and open that file. Okay, let's see what the compiler says. The compiler says that I haven't, so that you'll get used to how to compile. If we look at it, it says in accept, I had an error somewhere not declared in line 38, initializing arguments, argument 3, an error. It says it should be sock line T, and in my case, let's go to that line first. In my TCP C line 2, No, it's there. Oh, of course. I have some invalid characters here, first of all. Okay, then it says my MSG is not defined. Well, let's define it. This was an example that was not building. Defined max message 300. So I don't have that problem anymore. What return error? Error is not defined. Let's just return -1. In that case, and the second error -2. And then it said on line 37 that we had an error. Okay, I still have some invalid characters here. That's why I'm using this editor, because this source code was actually transferred from Windows and it has some invalid characters on it. Okay, let's delete this. Okay, and let's delete this as well. Okay, it's done there. So it says that on my accept call, this argument, the third one, it should be socklen. If I look at it, it should be socklen T type. Now, this is just a type def to the same integer that I have declared, like I have declared here. But because C++ is very picky to types, you need to do this because it's the same thing. Okay, the C++ probably if I would have compiled it with GCC, it won't have complained, but C++ is a strong typed compiler, so it needs, you can see here, socklen T. If I stand over it, it's a type def to unsigned int. So it's exactly the same thing. I mean, it complains because I declared it as an int, not unsigned. But this is most likely the same thing as this one, only that it should look at that integer as unsigned. So I do the cast there, return -3 error here, like that. Read, print, inet, hide that thing, write, and done. Let's try, save it. Let's try to compile it now. It tells me that I forgot memset is defined in C string, so it's quite chatty. So C string or string.hash, I think it should be the same. Oh, I forgot to include that thing. Should be declared here as well. Try to compile it again. And now it tells me line 36. Okay, let's forget about that. Line 36, 37 have some spurious characters. That's because I transferred from Windows. So 36 and 37. 36, I think is no, if not, it will be this at the beginning of the line. That's that red character, so I'll put it there. Okay, so I cleared it. It's not there anymore. Try to compile it again. Okay, so success. I was able to successfully build my server, and it's there. Let's do the same with the client. Okay, I can see I still have those spurious characters there, so I will go and delete them. Okay, they'll go away. They go away. Let's try to build this one, see what is happening. And we have some errors here, we will see. G++ -o client, my TCP client C. Okay, so again, let's go again and see what is happening. Oh, come on, not that many. memcpy, SYN family, SADDR. There is a problem here with some includes. Okay, this one. There's a problem with that one. I know I should include from the other one, from the other case, string or C-string for that matter. It's C-string because it tries to use the C standard library. String does it as well. Let's try to build it again. I still have lots of errors. 23, 29, 39, 47, that will be spurious characters. So 23, remember that, 39. So 23 spurious character there. 29. 39. Okay. 47, there was something as well. 47. Yeah, 47.
No, it's on the printf line, the quotes.
The quote, yeah. You've been to the lab.
Yep.
Yeah, so it's the quote. Let's take a look at this. Compile it again, and we still have some error. It says exit was not declared. Take a look. Don't be scared whenever you get a bunch of errors, but only look at the beginning, because what the C++ compilers are doing, for those of you that are not used to it, is they are actually splitting the first errors, and then they try to recover from those errors. So they try the syntactical analyzer and the semantical analyzer. The lexical, the syntactical analyzers are trying to recover from those errors. And why they try, if you really have an error, while they try to recover, they get into more and more errors because they get confused, and then you get lots of errors. So the errors by the end are not so meaningful as the one at the beginning. So it says exit was not declared. How should I do that? Well, man exit. It tells me I should include this, and probably I haven't done it. So let's copy and go there and include it. Okay, let's build again. That's this thing. Okay, and I'm using a client and a server. What the client does, if I call it without any argument, it tells me I should pass it 2 arguments: the server and the text to be sent to the server. Now, my example here, if we look very fast into it, my TCP client takes a host name as the first argument. It converts it, as is shown you during the class, to an IP address. Then it tries to connect to port 1500 on that IP address. It creates a socket, it tries to connect, it writes the string given as the second argument. It should have been, and this should have been the len of the second argument, and then it reads back, and there is an error here. As you can see, connect, it returns me an error status. But connect call does not return a new socket. So this has been an error. I think this source code has been given as a test to some previous years of study. So I'm not using the socket. I should have used that here, and I
also inside the strlen, we shouldn't have the +1 there, but outside.
Yes, we have string length from my string +1. Well, my string +1 does nothing, is nothing, but here I will do that. Anyone can tell me why +1 here? If you take a string like this, its string length will be 1, 2, 3, 4, 5. But you also should contain in it, you also should send over the network, if you want to send a valid string, that 0 at the end. So that's why it's string length +1. I need to send over the network the complete string. So read from the socket into my message, into this one, which is already a pointer because it's a vector, and print it back to the standard output, and then close the socket, not the error code returned by the call. Okay, and the server It accepts the connection. Let's hope it doesn't have the same errors. So it returns a new socket and it reads from the new socket. It displays from whom it got the message and it writes to the new socket back. And then it closes the socket and then it goes back to while and it accepts the new client. So my server, shortly what it does a while indefinitely, this one. Indefinitely, while one, print an error, accept, do some stuff with the client, close the socket and go back to accept. What we see as a behavior is that while I'm chatting with this client, I'm not doing anything else. I'm not able to accept any new client. So this is not a multi-client capable server. That's why it's called iterative, because it handles one client at a time. But let's go and run them. I will open another terminal here so that we're capable of seeing what is happening in both of them. I'll run the server here, server. Okay, so the server tells me, okay, I'm waiting for data on port, whatever. And let's write a client 127.0.0.1. And it says it knows the port because the port in the client was predefined as well. So it's fixed as this one. I don't need to give it as argument. So, and passing it to text. Has apples. And we still have some problems here. Mother has apples. I read that.
You didn't recompile the client code.
Right, so G++, that's a good thing. And okay, so what I see that I took this, I connected to the server, took that text, send it to the server, and the server says, okay, I received from 127.0.0.1 port, whatever this port is, 33520. Mother has apples, and I sent back, and the server sends back that data, and the client gets it and displays it. Now, I see some error in my TCP server. It says TCP, and should put a space here. TCP port, like this. So, okay, if back the server, G++ minus O server, my TCP server, and run it again. Okay, so address already in use. Now, you've got this error with address already in use. What is happening is when you close the server which is listening, we have this command, -a tn. That means netstat. You can look at the status of your socket machine. A means all sockets, T means TCP, and N, do not try to interpret these numbers as, try to figure out port 53 what it is. It will give you a textual representation. For example, 127.0.0.1 will be, if you don't put N, it will be localhost. We can try that if you want. You say localhost domain and so on, so on, so on. I'll put N because I want to see if port 1500 still appears here. What is happening, we're already into the break, just 1 minute and I'm finishing. What is happening is that while you're closing a socket abruptly by pressing Ctrl+C or killing the process, the TCP and the operating system will still keep that port allocated for some time. Why? Because you might still have data traffic coming from a different machine across the internet, and the operating system doesn't want to allow a different process to bind to the same process, to the same port right away, so that the new process succeeds, and then it gets some spurious data that belong to the previous connection. So if there are 20, 30, 60 seconds or 1 minute, 1 minute and a half, it depends on the operating system that the port is not available. Right now, if I would run it again, probably it should be running, okay? So do the same thing, and now I have all the stuff properly displayed and the data sent back. I can connect with another client. I can connect with another client and change the text. Now my server, it's iterative, as I told you, because it accepts client, handles them, and while it handles them, it cannot do anything else. And the last thing you should know is that these calls accept, read, and write are blocking calls. We will see that next lecture. That means accept, it will block the execution of your process until there is a client that connects. This means it's a blocking call. The server would not advance from this point on until you have a client connecting in. The read call on the other side, it won't proceed. It will block here until you have some data sent by that client. So while you don't have any data, the server would just stay blocked here. So that's why the server is not able to handle multiple clients at the same time, because it blocks here, and it only unblocks when it ends with a client. So these calls are blocking. The same happens on the client side. If you read something, the call will block. When you connect here, let's put this larger. When you connect here, this call will be blocking until either you manage to establish a connection or you get back an error. Nobody's listening or something happened on the other side. Okay, so these are blocking calls. Keep that in mind so that you know when you're programming something that those calls or the execution of your program will stop there until something happens. So with this in mind, sorry for keeping you during the break. We will stop here and we will continue during the lab and go on and with the implementation of the applications that you will need to do for today's lab. Okay, lab 1. Lab 0 was the virtual machine. Lab 1 will be actually writing your own code with some iterative servers and clients. Iterative means they are able to handle just one client at a time. In this approach that we had here, the server is not able to do that. Okay, any questions? And we stop here. I see there I have some messages, maybe. Yeah, okay, sorry, better boring. Yeah, I agree with you. I know I handled that with probably most of the groups, study groups have already handled this. But as there was one group, you were sacrificed for the others. So I had to pass through through this part. Feel free to tell me, okay? Open your micros now because the class is finished. I will stop the recording. Feel free to tell me, to stop me whenever you think that is something that